Hello students, welcome to Educate. We are going to continue with chapter 6 of class 11th physics. In previous lecture, we have done till 6.6. Now we are going to continue with question number 6.7. Two particles each of mass m and speed v travel in opposite directions along parallel lines separated by a distance d. Show that angular momentum vector of the two particle system is same whatever be the point about which the angular momentum is taken. So consider this is x-axis and here there is one particle of mass m. Its velocity is v in downward direction and its distance is x from the origin. There is another particle here of same mass, but it's moving in opposite direction with velocity v, and say this separation is d. Now as per question, we have to see that angular momentum of the system is independent of x, because this is a point about which we are taking angular momentum. So what is formula for angular momentum? L equal to mvr. Or in vector form, if we write vector L equal to vector r cross vector p. So here, if this is y-axis, so angular momentum L if we find, so angular momentum L will be angular momentum due to first body, then due to second body, L1 plus L2. Now L equal to this r cross p. So here r will be x I cap and p is mv and its direction is toward negative y. So here minus j cap. Now for this, its position vector up to here, so r will be x plus d times I cap and then cross p. P will be mv and then direction will be along j cap. Now let's simplify what we are getting. X mv, let's write here negative sign, and then I cross j plus here x mv mxv times I cross j plus mvd I cross j. I cross j equal to k, or these two are same with opposite signs, so you can directly cancel them. What is left? mvd and I cross j, and I cross j equal to k. So mvd k cap. Here x is not there, so the question was two particles each of mass m and speed v travel in opposite directions along parallel lines separated by distance d. Here one is traveling in this direction and the other is traveling in this direction. They are parallel to each other and the separation is d. And show that the angular momentum vector of the two particle system is the same whatever be the point about which the angular momentum is taken. Now if we shift this, suppose we consider like this, up to here we take y and then Same situation we consider. So this is M, V, M, V, and suppose this separation is D. So again, Y will not come. So that is why they are saying that the point about which angular momentum is taken is irrelevant. Only the separation is important. So we have got the answer. Now we are going to see this question. This question says a non-uniform bar of weight W is suspended at rest by two strings of negligible weight as shown in figure. The angles made by the strings with the vertical are 36.9 degree and 53.1 degree respectively. The bar is 2 meter long. Calculate the distance d of the center of gravity of the bar from its left end. Here, there is one very interesting point. What is that? So, let's write 36.9 is roughly equal to 37 degree. This is 90 degree, this is 37 degree. Although value will remain same. If this angle is 37 degree, then here Pythagorean triplet will hold such that this will be 3, this will be 4, this will be 5 for 37 degree. And suppose this angle is second one. If you take this 53 degree, almost 53 degree, then again same Pythagorean triplet will hold, but here it will be 4, here it will be 3 and 5. The same concept is being used here. You don't have to use calculator. You have to keep in mind that for 36.9 degree, we can use this. For 53.1 degree, we can use this. Then question will become easier. So let's see what is happening here. In this diagram, if we write here tension, suppose we write tension T1 here, then it will have two components. One along this line and another along this line. This angle is theta, suppose. So this angle with theta means 36.9 degree. So in this direction, it will be T1 here cos theta, where theta is 36.8, and in this direction it will be T1 sin theta. Now if this is T2, then we extend this. So one component will be in this direction, that will be T2. This angle will also be 53.1 degree. So T2 cos, say phi, here phi is 53.1, and this will be T2 sin phi, correct? So what do you observe? If this rod is not moving, means there is translational equilibrium, then T1 sin theta must be equal to T2 sin phi. This is first condition. T1 sin theta, theta means this 36.9 degree must be equal to T2 sin 53.1 degree. Now, as I told you, if you take this 36.9, then this will be 3, this will be 5, this will be 4. So this will become T1 into sin this 3 by 5 equals T2 into sin 53. 53, if you take 53.1, so this will be 4, this will be 5, this will be 3, so 4 by 5. So you have got one relation, 5 will cancel out. So either you get T1 upon T2 from here, so that will be T1 upon T2 will be 4 upon 3. This is one relation. I think this point is clear. Now, if you consider a rotational equilibrium is moment about this point in this side. So moment about W must be equal to moment. Here moment about W on both sides should be same. So you can say this distance is suppose D. So this will be 2 minus D. So moment, you understand, force into perpendicular. So distance D multiplied by this T1 cos theta, we will put 36.9, must be equal to D2. Here not D2, we can write it as 2 minus D. So 2 minus D times sine phi. One relation we have already found. Here there is another relation, times 2 minus D distance into T2. Sorry, this is torque, or if you want to see, I can write it clearly. So here this is D, this is 2 minus D. Here there is T1 cos theta, and here there is T1 cos phi, and here there is weight W. Right? So I am writing this multiplied by this, and then this multiplied by this. So thing is clear. So what we have got? D into, so previous relation, if you remember, once again I can explain everything systematically so that thing may become clear, because this question is assumed to be little tough, but don't worry, you can easily do. So this is T1, this is T2. Here we extend this line and either make it 90 degree, then this will be same angle, or here just do this and this angle will be same. Let's write it as phi for time being. So this will be T2 cos phi, and here T2 sin phi, and here again this will be, this angle will be say theta, and so this will be T1 cos theta, and this will be T1 sin theta. So as I told you, for translational equilibrium, this rod should not move. So these two forces, this and this, must be same. So this is first relation. T1 sin 36.9 degree must be equal to T2 sin 53.1 degree. And then we can put the values. T1 sin 36 means 3 by 5 equal to T2 sin 53 means 4 by 5. Or we can get the relation from here, 3 T1 equal to 4 T2. So this is first relation. We can write T1 upon T2 equal to 4 by 3, etc. So that is one thing. And for rotational equilibrium, as I told you, so W must be balanced by here. So about this W, we are taking the moments. Moment means force into perpendicular distance. So here this distance is D, and this is T1 cos theta force. So D times T1 cos 36.9 degree equal to 2 minus D, because this length is total 2 meter, 2 minus D cos 53.1 degree. Here we have written sine 36.9 degree, that is 3 by 5. So obviously this will be 4 by 5. D into T1 into 4 by 5. 2 minus D, here T2 is missing. So T2 into this will become 3 by 5. Now again, either we can put the value of T1 from here, and then we can evaluate T2 in terms of D. So whatever you adopt, whatever method you adopt, that does not matter. Just you have to get T1 and T2, right? And when you have got T1 and T2, after that you can get D. So we are going to evaluate it. So do one thing, get T1 upon T2 from here, that is 4 upon 3. And also get T1 upon T2 from here. T1 upon T2 will be what? You take this here. This is 3 by 5 into 5 by 4. Is it okay? This is 2 minus D divided by D. So this is one relation, this is another relation. Now equate the two. 4 upon 3 equal to here 3 by 4 times 2 minus D upon D. Now simplify. So 16D equal to 9 times. 16D equal to 9 times 2 minus D. So you will get 16 and 9, 25, 18 by 25, D equal to, you will get 18 by 25. So that is the answer. I think you have understood. Now, let's consider this question. This question says, a car weighs 1800 kg. The distance between its front and back axle is 1.8 meter. So we can say this distance is 1.8 meter. This is front, this is back. Now center of gravity is 1.05 meter behind the front. This is front axle and this is back axle, and here the center of gravity lies. So this distance is 1.05 meter, total 1.8, so 0.75 meter is this. Up to here there is no problem. Now its center of gravity is this much behind the front axle. Determine the force exerted by the level ground on each front wheel and back wheel. So here we can take a moment and then evaluate. Consider it. So let's consider here normal reaction on front wheel, and here normal reaction on back wheel. Now what will happen? Weight will be balanced by normal reactions. So we can write normal reaction front wheel plus normal reaction of back wheel is balanced by W. Up to here there is no problem. In our question, weight is given. So here 1800 multiplied by 9.8 Newton. So this is, say, equation number 1. Now let's consider rotational equilibrium. So we can say for rotational equilibrium, force, here we are going to take torque, so 1.05 into NF, right, must be equal to 0.75 into NB, right. So here we can get the value of NF and then we can place it here to get NB. So after, just take 1 minute to evaluate it. So after evaluation, you will get NF equal to 7358 Newton, and N back will be 10290 Newton. Since there are two wheels in front and two wheels are in back, so each front wheel will get half of it. So you can say 7350 divided by 2 for each front wheel and 10290 divided by 2 for each back wheel. So that is the answer. Now let's consider next question. Question is, torque of equal magnitude are applied to a hollow cylinder and a solid sphere, both having the same mass and radius. The cylinder is free to rotate about the standard axis of symmetry and the sphere is free to rotate about an axis passing through its center. Which of the two will acquire a greater angular speed after a given time? So here in this question, we have to consider the moment of inertia of the two bodies. So moment of inertia of a hollow cylinder, say I cylinder, will be equal to 1 by 2 mr square, and moment of inertia of sphere is equal to 2 by 5 mr square. And if you remember, dl upon dt is equal to torque here. We can apply tau equal to, if you compare F equal to m a, so corresponding values I into alpha. So for first one, torque is same, so we can say I1 alpha 1 must be equal to I2 alpha 2. Right? So I1 for first 1 by 2 m r square into alpha 1. Right? We are taking it as I1 and its angular acceleration is taken as alpha 1 for cylinder, right? And cylinder. So here it will be 2 by 5 m r square times alpha 2. So what a relation you are getting? mr square will cancel out. Alpha 1 is equal to 4 upon 5 alpha 2. So here clearly alpha 2 is greater than alpha 1. Now omega equal to omega 0 plus alpha t. If we assume that both start from a rest, so first term will not be there, so omega will be equal to alpha t. Time is same, so omega 1 equal to alpha 1 t and omega 2 equal to alpha 2 t. But alpha 1 is less than alpha 2. We have seen from here that alpha 1 is less than alpha 2. So if alpha 1 is less than alpha 2, time is same, then obviously this omega 1 will be less than omega 2. I think you have understood. Now There is another question. A solid cylinder of mass 20 kg rotates about its axis with angular speed 100 radian per second. The radius of the cylinder is 0.25 meter. What is the kinetic energy associated with the rotation of cylinder? What is the magnitude of angular momentum of the cylinder about its axis? Do you remember the formula? So here first point is, what is the kinetic energy associated with the rotation of cylinder? So first of all, you should know rotational kinetic energy. So rotational kinetic energy is given by half I omega square. Here angular speed omega is given, I is not given, and we are talking about cylinder. So cylinder has I as 1 by 2 mr square. So we can put this value here. So kinetic energy rotational is equal to 1 by 2 into 1 by 2 mr square times omega square. Now let's see whether values are given. M is given, radius is given, and omega is given. So try to evaluate it. So it will come out to be 0.625. Then this is kinetic energy. So unit, you have to write what will be the unit. Will it be joule? I think this is wrongly written. So let's rectify it. No, this is not correct value. This is the value of this 0.625 kg meter square. And when we write these values here, 1 by 2 into 0.625 times omega square, omega is 100 square, then we will get 3125 joule. 3125 joule. So I think this is clear. Now further, what is magnitude of angular momentum? So angular momentum can be found L equal to I times omega. So I, we have this much. So 0.625 into omega is given in our question 100. So this will become 62.5 kg meter square per second. Kg meter square per second. I think you have understood. Now we are going to take next question. Next question says, a child stands at the center of a turntable. Simple. Here in absence, I2 is 2 by 5 times I. 200 divided by 2. So initial kinetic energy, 5I times this is 100 square. So I will cancel out. This will become 5 into 1600 divided by 2 into 100 into 100. You can simplify. You will see that kinetic energy increases. So for this, here what the child is doing, here child stands at the center. Team Educate